In this video we're going to take a look at solving trig equations. So one of the things that will happen as you move on is that all the equations are going to be mixed together, and you're going to perform some calculus work and then have to solve whatever equation you're faced with. It might be quadratic, it might be linear, rational, radical, log, exponential, trigonometric. Okay? Different types of equations have different general approaches and different details that you need to worry about. Sometimes you want to move everything to one side, set it equal to 0. Sometimes you want to isolate an expression. Right? So when you see square roots, generally you want to get the square root on one side and everything else on the other side. Same is true for exponentials and logs, and we're going to do the same thing for trigonometry. So when you see a trig equation, like in part A here, you want the trig expression by itself, which it already is in part A. In part B, you're going to want this trig equation by itself, which means anything that is not part of that trig equation itself, right, inside of it, needs to be moved to the other side. Okay, so the first thing we're going to have to know is anytime we have a trig equation, whether it's sine, cosine, tangent, or one of the other three functions, that we're going to have to isolate the trig expression, right, the trig function. Then what we're going to always end up with is that trig function is going to equal one of the basic values that we saw in our table. So we have to come up, or we're only going to be given questions that use the common ratios. Otherwise, you'd have to go to the calculator and approximate. So it's not a coincidence that this one is a half, right? Let's just sort of hold off on the negative sign for a second. But you're basically, going to start off by asking yourself the sine of what angle is a half, right? First, let's get the reference angle in the first quadrant. Then we can use rotations of this to deal with the negative sign. So, you can always pull your table out if you forgot it. You can always do 0, a half, root of 2 over 2, root of 3 over 2, root of 4 over 2, right, which is really 2 over 2. I started writing before I finished, which is 1, right? This is our sine theta column, right, as we go from 0 to pi over 6 to pi over 4 to pi over 3 to pi over 2. I went over that in a previous video. But one way or another, whether you memorized it, used a calculator, did some exploring, one way or another, you want to realize that the basic reference angle is pi over 6. Okay? So any theta that solves the equation in part A here is going to have to be some rotation or multiple of pi over 6. Okay? Now, because we have a negative sign here, we don't just want to make sine positive a half, we want to make sine negative a half. So where is the sine negative? Right, sine is negative down here and down here in the third and fourth quadrants. Remember, the sine is the y-coordinate. Y-coordinates are going to be negative below the x-axis. So what we really need is all of the times between 0 and 2 pi, right, which is one full rotation around, that the sine is a half, some version of pi over 6. Right, that's in the third and fourth quadrant. So again, get your reference angle, 6 pi over 6, call this 12 pi over 6, right, 1 pi and 2 pi. And then you can place your angle here. This is one more. This would be 7 pi over 6. And then this one here is actually one less from 12 pi over 6, so that would make this 11 pi over 6. Okay? So the two values for theta between 0 and 2 pi, right, they're going to satisfy this equation are 7 pi over 6 and 11 pi over 6. Okay? So when you're solving a trig equation and the variable is the angle, right, then your answers have to be angles, and they should generally be multiples of those reference angles if they're not in the first quadrant. Okay, so in this case, you just had sine of theta. The negative sign you had to deal with, you always start with the reference angle and the ratio corresponding to it, and then use the positive or negative sign to decide how many of these are solutions. Now, the thing we have to remember with sine and cosine and tangent functions is that there might be more solutions. And the reason there might be is you're rotating around a unit circle, and every time you do a full rotation, you start over and you get more angles. So when you look at something like here in part B, right, 2 cosine 2x minus 1 equals 0, there is no restriction on the domain, right? So this goes on forever. So, you know, you might get one answer in the first rotation and then another answer in the second and another in the third. You could also go backwards and get answers, right? There's going to be an infinite number of solutions here because every time you rotate around the circle once or twice, right, depending on the situation here, you're going to get solutions. Now, what I said before is we have to isolate this cosine of 2x. So the first thing we need to do is add 1 to both sides. I might just erase this wavy line so it doesn't get in the way. Right, we're going to have 2 cosine of 2x equals 1. Right, then we're going to divide by 2 on both sides. So we'll get cosine of 2x equals a half. Right? Now, since I already have this table here partially filled out, right, I know that this cosine column, right, is going to be the reverse of the sine. So pi over 3 is really the one I'm interested in, right? And I know that the cosine of pi over 3 equals a half. Okay? Now here's where things get a little bit more complicated because it's not just an x in this case, it's a 2x, right? So 2x has to equal pi over 3. If 2x becomes pi over 3, right, then the cosine would be a half. Okay? Now we do have to check the plus or minus. Right? So cosine is positive here and here, right, because it's the x coordinate. So one situation would be if 2x equals pi over 3, then the cosine should be a half. And dividing by 2, that means x would be pi over 6. Right? Now there's another time, right, that we would deal with that, and that's down here. Right? So in terms of pi over 3, right, this is 3 pi over 3. This is 6 pi over 3. So the next time that cosine is a half is at 5 pi over 3. Right? Go back 1 pi over 3 from 6 pi over 3. That'll put you in the fourth quadrant. That'll also be a half. So again, this 2x, maybe I'll use just a different color here, right, could also be 5 pi over 3. So 2x could equal 5 pi over 3, which means x would be 5 pi over 6. Okay? Now, what's happening here is this 2 is making us go a little bit differently through the unit circle, right? We're going to finish 2 rotations in the course of what normally would have been 1 rotation. So we have 2 answers here. The question is, you know, what about the next time, right? When's the next time we're going to go around? We got pi over 3, then we got 5 pi over 3. The next time would be 7 pi over 3, right? This would be 7 pi over 3. Would be the next time around. So we could also have 2x equals 7 pi over 3, right? And that would give us that x equals 7 pi over 6. Right? Right? The next time around, if we kept going, right, this would become 6 pi over 3. You need 4 pi, so this would be 12 pi over 3. Go back 1, it would be 11 pi over 3. So we could have 2x equals 11 pi over 3, which means x is 11 pi over 6. Okay. Now we could sit here and kind of go on forever, ... until we feel like we've established a pattern. There actually is a little bit of a pattern here, but it may not be quite so easy to see. The presumption is you've done this at some point before and might remember that, you know, when you have these infinite rotations, you add something like plus or minus 2k pi, which means every rotation you go around, you can still get the same basic angle. So when you add 2 pi or 4 pi or 6 pi or 8 pi, you're always going to end up in the same place. In this case, if you notice, this pi over 6 and this 7 pi over 6 are exactly pi apart, right? 6 pi over 6 plus 1 pi over 6 is 7 pi over 6. And the next time you went around, right, this would become 13 pi over 3, which is exactly 6 pi over 6 up from 7 pi over 6. Because you're going twice as fast, every time you go pi radians, you're going to do a full rotation. So you're going to go up and down this one here. Every k pi, you're going to get a valid answer. And similarly, if you look at the 5 pi over 6 here and the 11 pi over 6, they're also 6 pi over 6 apart, which is exactly pi. So, you know, this gets a little bit more complicated. I think most of the time in calculus you're going to see sort of finite intervals where you won't have to deal with this necessarily, but one of the answers will be pi over 6 plus k pi, and the other answer would be 5 pi over 6 plus k pi. Now k can be any constant integer, plus or minus, so you don't really have to do plus or minus k pi. You could let k equal -2 or -3 or -1 or whatever. But in this case, there's really two angles within the pi radians, and then because you're going twice as fast, every time you go pi, you're really going 2 pi according to the equation, right? Which will put you back in the same exact location and give you the infinite solution. So there's really infinite solutions. Sometimes you do plus 2k pi if there's no sort of frequency frequency effect here, but in this case there is. Okay. Now the basic thing, I don't want you to get too bogged down in those details about the plus k pi. Basic idea is, get your trig equation equal to a ratio, figure out the missing angle, and then see how many of those you have to come up with to fit within your interval. Okay, solving trig equations is always, well, no, I shouldn't say always, but for most people it's more complicated, it's less familiar, it makes you stop and think a little bit, but if you can get that general principle down and that general strategy, it should be a lot easier to do. Okay, you'll probably solve a lot more linear, quadratic, and other types of equations, but every once in a while you have a trig equation to solve, and at least the first few times they come up, you might want to refer back to some notes like this or something from your old Precalc book to help familiarize yourself until it becomes hopefully second nature.